So this is G484 homework booklet question 6. Starts off with a little bit of G481 really, calculate the kinetic energy of the car. Very straightforward use of a half mv squared. It's absolutely straight. Here's the equation, throw the numbers in, calculate the answer. No rearranging, no messing around with units, so hence the single mark there. And it comes out as 3.5 times 10 to the 5 joules. A little bit more interestingly, again G481, looking at the car safety section, calculate the average braking force on the car, stating any assumptions that you've made. So the basic idea we used a lot during G481, the car safety, was that when you stop, you're doing work and converting energy from that kinetic energy that we had previously into thermal energy, and calculating the thermal energy might be messy, but what we can do is to calculate how much is transferred, because the energy transferred is equal to the work done. So we end up with the work done, the braking force multiplied by the distance we travel while we're braking, must be equal to that energy, the 3.5 times 10 to the 5 that we had previously. Rearrange that and we get that the force is that energy divided by the 40 meters of the braking distance, and getting us to 8.8 times 10 to the 3. Now in essence really the assumption is that all of that loss of kinetic energy is as a result of work done by the brakes, but what else could have done any work? The most obvious solution to that would be some air resistance. So the assumption they're looking for is that there is no air resistance involved. Part B then does move on into the G484 stuff, and it looks like a very straightforward MC delta theta. If we start simply with E equals MC delta theta, we can rearrange to delta theta is E over the mass 1.2 kilograms times the C, the specific heat capacity of the material. We've got two choices here. You can either think of, where does this 4 come from? You can either think of that each brake's got to get rid of a quarter of the energy, or you can think of the total mass of brake, which was the mass of one brake, times 4. One way or another you end up with that same sign, same sum, sorry. So either thinking of it in terms of the total energy divided by 4 is the amount of energy that's got to be dissipated by each brake, and then multiplying that by one brake, and C on the bottom there, or thinking of it as the total amount of energy and thinking of that as the total mass, 4 times 1.2 kilograms times there, and we end up with a temperature rise of 140 degrees C. So moving on then to the more discursive part, Stein explained 2 reasons why the actual temperature rise will be different from that. So in there what we've done is we assumed first of all that all of the work was done by the brakes, so that won't actually be the case. Air resistance will do some work, and therefore the amount of kinetic energy that will be transferred to thermal energy in the brakes will actually be less. And secondly, we've assumed that all of that thermal energy stays within the brakes, and of course that's not true. Heat will be lost from the discs since they're hot in their surroundings, so they'll go on to heat the air and so on. Key thing they were looking for there, and which is worth remembering for other questions, is yes, we've got heat loss from the lost from the discs, but that's because they are hotter than the surroundings. Finally then, it's asking for a modification to the design of the braking system to reduce the temperature rise. So we could have we could either look back to our equation where we were calculating the temperature rise. How could we get a smaller temperature rise? We could have a higher mass. We could make those brakes bigger, make them of a bigger material. We could make them of a material with a higher specific heat capacity. All of those things would reduce the temperature rise for them still doing the same amount of work and holding on to the same energy. The other thing we could do would be to actually increase that heat loss from the brakes. In practice, disc brakes are drilled holes in the discs which designed to increase airflow. In fact, car brakes are often two surfaces with essentially holes running through the whole way through to the centre and out the other side. Lots of different ways of increasing airflow to cool them, so although they'd still be doing the same amount of work, that heat would be going out the whole time while they were cooling. So that was G484 homework booklet question 6.